Hello, welcome to video 49 in the lecture Advanced Mathematic Modeling. So with this video now I want to leave the theory of random walks and movement ecology, even though a lot could be said more about this. But I want to continue more these ideas about scaling and power laws that we have encountered so far when we looked at power law distributions and looked at behavior at different scales. And there is a very important can you say application or consequences, or if you follow up these ideas a bit more, and this goes under the name of fractals. And so I don't know if you ever heard about fractal dimensions, so objects which have a strange dimension. And so we want to know, so what is the dimension of an object? Dimension of, let's say, a physical object. And now you could wonder, why do we ask suddenly about some physical concepts about the dimension? But as we will see, the concept of dimension is closely related to concept of scalings and the ideas that we had before in this lecture. And actually, which is funny enough, this is the first question I learned when I had my first lecture in theoretical physics. So the professor this time, he started with this. He wrote this question at the blackboard and asked us, what is the dimension of the physical space? That's actually what he asked. What is the dimension physical space? Now the obvious answer is 3. So we have 3 dimensions. Physical space has 3 dimensions. And now I will leave aside this quantum field theory aspects or string theory. When you ask modern theoretical physicists, they might tell you that at very small scales the world is consisting of strings and might have a dimension of 10 or something similar. And I also don't want to look here in relative spatial relativity, the theory of Einstein, where you have space-time. So actually, so space and time are maybe a common object which has a four dimensions. So we don't want to look at these things just as a normal physical space, and then you could say, yeah, it's 3 dimensions. But so first, now I could ask, so first, where do you know this from? How do we know that the space has 3 dimensions? And what actually do we mean by this? And then, so typically also one would say the dimension is the minimal number of informations needed to specify the position of an object. So, and then you could also say, let's take here an area, and then we say, okay, that's a 2-dimensional space. And how do I know this? Because let's say I have an object somewhere here. So that's my object. And if I want to know the position of this object, I need two information. I need to know its horizontal position and I need to know its vertical position. And with these two informations I can obtain I can specify the position of the object. I could also have done it differently. I could have taken polar coordinates and have given an angle and a radius, but still I would need two positions. Now, if this is a mathematical vector space, you can easily prove then that this dimension is 2. But I mean, that just goes for vector spaces in math. But what about the real space? So if we have now a real position of an object, let's look at, say, the room in which you're sitting in the moment. How do we know that this is three-dimensional? So, okay, you could say I can place try and error and see how can I find or specify the position. So I need x and y coordinate and the height. But this doesn't tell you, maybe that's only for typical positions in the room. Maybe there are some hidden spaces in the room where you need 4 positions to find an object. Or maybe there's some easy points in space in your room where you need only 2 positions, informations. So how can we know about this? So and now in science, the better question is usually, can we measure the dimension? Because that's typically how in other objects in science we obtain the value of something that's of interest of us. We define a measurement procedure. Or measurement instructions. And then if you do this measurement, then you obtain a number, and this number gives you the value you want to have. Now the question, can we define a measurement instruction for the dimension of an object or of the space? So we would have, this measurement instruction would say, if we have an object, so this object could be, here an object, this object could be now something like a stone or an animal or the whole space. And now we make some measurement of this. And then we want to get a number d. So this measurement then would be a function d, which goes us from the set of all objects. When we make here, try to make an S which is like the set of all objects, because this is an object S, so the set of all these S's, and this set will be mapped into the natural numbers, because we assume here the dimension is an integer number or natural number because it's the number of informations. So can we find such a procedure? And now when you think about this, that's not so trivial to find such a procedure. So maybe first we should think, what do we do when we make a measurement in general? So again, I mean, this sounds like a first lecture in physics, not in modeling, but bear with me. We will come, the connection to this lecture will come soon. So let's first see, what is a measurement? What do we mean by this actually? And to make it simple, so let's first Measure length. How do we measure length? So let's say we have here a line, and we want to know what is the length of the line. So how can we measure this? And so what we do first, we need take a scale. We need a scale. That's some smaller object, and the scale is characterized by the size of the scale. This is this epsilon. And now we take the scale, so like this could be a small stone or a small whatever, small physical object. And now we take the scale and see how many of the scales do we need to cover our line. Maybe I make the scales here to make it clear in blue. So you will see we need a little bit more, so the large scale will be a little bit behind the line. And so and then we say the length of this line. So we count now. So take a scale. So when we make a coverage, we call this a coverage of our line. Or better we say covering. We make a covering of our line, and this covering means we find an arrangement of scales so that every piece of the line is covered, and find the minimal number of pieces needed to make such a covering. Minimal number of scales, and this number we call n, needed to cover the line. And then we say the length, we call it L, equals n in units of our scale epsilon. So when we make a measurement, we need a scale. The scale defines us units, and so we cannot know what's actually this tells us, teaches us some modesty. We don't really know what is the length of this. We can only compare the length of the line to something else, and this epsilon, or maybe we call this, so what can you take? Let's say take example, take a foot, and then you go your whatever object you have, your garden. You see how many foots do you need to cover the whole garden, and then you have the length of your garden in feet. And so we can only make measurements relative to a scale, and then that means all physical measurements gives us results in units of something. Now you can say, how can we measure? Actually, maybe for now we can also use the same thing, not only for a straight line. So this would be, not only that would also be the thing if you want to have a distance. So if you, let's say, works also for a distance. Let's say we have an object A, we have an object B, and I want to know what is the distance between these objects, which I call L again. And then we try to find a coverage, a covering of such small scales. Now you see this will not be the optimal thing until we covered, we made a continuous line from A to B, such a covering, and see how many objects we need. And then we look for the minimal arrangement, the minimal number of objects to go from A to B, and that we call the distance from A to B. Yeah? Works also for distance. Yeah? So we can measure distances, we can measure lengths of lines, but it works also for curved lines. Let's say we have a line which is like this, and we want now the length of this line. Of course, we do the same thing. We make a coverage. Now we have, of course, to be careful that these things are always straight line segments. So you see, maybe I make a very curved thing and make a big, so you see we of course make some this scales will deviate from the real line, but we still can find how many objects we need. For example, in this here we would need 4 scales, and then we say the length of this black line is 4 in units of hours. Oh gee, sorry, I forgot to shift. So let's say we have this curved object here, and better is to look at the big one. So we again make a covering. The covering will not perfectly overlay with our line here, because but it doesn't matter. We need how many of these scales we need to come from the first place to the end. In this case we would have 4 such scales, and also then we say this curved line has a length of 4 in this case, length 4 in units of our epsilon. And in a similar way, now let's follow this thought, we can measure time. So what's the time between 2 events? E1 and E2. So we need again a scale. So we need a small time event, and we get this, for example, from oscillations. Yeah. And then you need something which oscillates, and every oscillation will have the same scale. And example, take your heartbeat. And then we call one heartbeat, we call this seconds. And now if we now I make here time axis. Here was event 1, here was event 2, Now you have to see how long does one heartbeat take. Maybe it's this time, it's one heartbeat, the second heartbeat, the third heartbeat. You need to cover the whole thing, and then we would say the time between event 1 and 2 is 3 seconds. So. So also when you measure time, you make a coverage, you count the number of covers you need, and then you give the time in units of your scale. Of course, now a second, the heartbeat is of course maybe not so reliable. It's the same here in spatial thing if you take food here. And then what you then say, okay, we take some object that we really put in a safe place, and we call this object a meter. Make a piece of steel or something, put it somewhere, and then we can always go there and look what is the size of this object, and then we measure something in meters, and that's more unified than the food, which is very variable between different persons. And here also we don't take as oscillation a heartbeat, which varies a lot actually. I mean, a healthy heart has a strong variation, but you could also take other more precise oscillations. We see, for example, take a day, take a day-night, and then we get the time in days, and then we say a second is a certain fraction of a day. Yeah? But this is now just making this more reliable, tuning, finding good oscillations, good scales, but that's how we measure things. Yeah? We take coverage and measure in units. Okay, so that was now lengths. Now in order to come to the topic of our lecture here, now let's measure an area. So now we start to get into the scaling ideas. So let's say we have here again this rectangle, and or maybe it's a different thing, a billiard here, for example, and we want to measure the area A. So then again we need a scale. And the scale is now some object which has a typical width epsilon. So the scale is a small two-dimensional object. I mean, we know we are now in 2 dimensions. It's a small two-dimensional object, but it has a certain width epsilon. And now we try to make a coverage of our billiard. Yeah, you don't even need to have a perfect lattice, we just need to make a coverage and make sure that we have everything we need to cover the whole thing. No? And now we need how many of these objects we need. We need n such scales. Needed. And then we say the area equals n in units of, and now since we're in a two-dimensional thing, the area of the small thing, this has the area epsilon squared, yeah, because we have a two-dimensional object. So to measure an area, yeah, so the area equals n times epsilon squared. So it's the same procedure as before. We make a covering, we measure the minimal number of scales you need to cover the whole object. And then the area is this number in units, but now it goes in units of epsilon squared. Now let's measure a volume. We have a certain volume. And we want now to know the volume. So we take a very small scale. And this has the volume of the scale equals epsilon to the power 3. And then we see now we put in the small things in here. Alright, so we and so on, and you see how many of these blocks we need to cover everything, and then we see the volume is the number of these objects times epsilon to power 3. And then of course there's differences if you try to make a good covering like with bricks, like you make a wall here. At the border you have always something which is on top. I mean, if you measure volume and you measure the volume of your bathing tube, you of course can take here a small glass and then put all this water in there, and you count how many glasses you have to fill in the whole thing, so until the bath tube is full. So this n is just a number how often you have to fill the glass in here. And then since the water is distributing equally, you don't have these problems of these arrangements. But the principle is the same, and you give the volume in which goes then with your dimension, your scale to power 3. Okay, so that was just basic physics, how to measure volumes, areas, times, distances. So, but how is this all related to dimension? And you see the dimension comes in this formula here. Volume goes n times epsilon to power 3, or in an area n times epsilon to power 2. I mean, that's actually the dimension. Yeah? So the generalized volume of a d-dimensional object how do we measure this? The volume of a d-dimensional object. And we say the volume equals the number of scales you need times the size of a scale to power d. Right? Because if you measure volume, you need e epsilon to power 3, for an area epsilon to power 2, and for a length epsilon to power 1. So, and now comes the trick. So how now when can we measure the main idea? So measure the volume at two different scales. So we have the volume, maybe of our object that we're interested, and first we measure it at scale epsilon 1, and we need n1 coverings times epsilon 1 to power d. But we could measure our object, so like that would be, for example, in cubic millimeters, Now we measure our object in cubic feet. So then we get a different number of coverings we need times epsilon 2 to power d. Now the volume should not change by doing this. The volume is not influenced by the way we measure anything. Yeah. So the volume is not changed by our measurement. And then we see, now we can just relate everything. Then this means these two numbers should be the same, plus minus measurement errors, and we come to this like that we have some, of course, it depends of course how much our scales extend beyond our objects, but so actually it should be here approximately because of these imprecisions, but otherwise we have n1 divided by n2 is approximately epsilon 2 divided by epsilon 1 to our dimension. Yeah. And now we have done everything we need in order now to know what's the dimension of the room we are living in. We cover our room with objects of different sizes, small objects and large objects. We see how many things we have to fill in, and from this we can calculate our dimension. So the dimension tells us how many or maybe formulated different. So we could say in the moment dimension tells us how do measurements differ at different scales. So, and now we have a measurement procedure how to measure the dimension, and it depends how objects behave if they're measured at a small and a large scale. So dimension tells us something, how do some properties of objects scale with size. And for this here I conclude this video, stop this video because it's getting too long, and we will follow up these ideas in the next video. Thank you.